we did the calculation and predicted this. We predicted it based on the model. Then we did TDSE to verify. And then the experimentalists got interested and did experiments to also verify. So this was an experiment, by the way. The experiments that I've shown are from my colleague Itzik's group. Okay? Several of his students are here representing the group, Payman and Travis and Bethany. Some of them were involved in these experiments. And you can see that there's C phase effects in the symmetry for this process. 5 femtosecond transform limited, chirped out to 21 femtoseconds positively, or 21 negatively. And you can see there's C phase effects here, right? Seeing red and blue stripes, that's C phase effects. Red and blue stripes. And here they're fainter, but they're still there a little bit, okay? So it looks like bandwidth really is an important factor, not just the pulse thing. Let me take a couple more minutes, because I want to address what Ken brought up. How can we use this picture to predict things for maybe more complicated systems? Well, I showed you this picture before. This was the multi-photon structure in dissociative ionization of H2. So let's say this is 3 photons and 4 photons and 5 photons and 6, for instance. Okay? Well, if we want to predict whether there's C phase effects, what energies will they be in this picture? They have to be between these photon peaks, right? Because it has to be, say, 4 and 5 photon interference, so it has to be in there. So if you want to see a spatial asymmetry, it has to lie in there. What does spatial asymmetry mean for this system? It means the electron going a different direction than the proton. Okay? So if the proton goes this way, the electron can go the same way or the opposite way. That would be spatial asymmetry, and that would happen here, 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 or there. Okay? So clearly in this case, you need a much shorter pulse to be able to see it, because there's not much overlap there. Okay? And that's just what I see over on the side. Now, relating to some of the things that Ken brought up, this picture, if you replace H2 by helium and, the alpha particle and 2 electrons, the picture looks the same. Double ionization, the picture looks the same. Okay? And so if you wanted interference, say to control the yield of double ionization, well, this photon peak has to interfere with that photon peak. So you need a really short pulse or really broad bandwidth such that there's interference between this guy and this guy. Okay? Then you can control the yield. Okay? You can use that same kind of logic for understanding, for predicting C phase effects in other systems. Now, yeah, there is more good stuff, but in terms of time, I should stop. Let me just say one more thing, because it again relates to what other people were talking about. We can do all the same things for 2 color fields, or 3 color, or 4, or 15,000, I don't care. Okay? If you can write a 2 color field like this, so this one has a phase and that one has a phase, well, this one could be the phase relative to that one, for instance. Well, if I can write it like that, then of course I can do a Fourier series, and I can do all the same analysis. So, Rabbit, the ATOS, AB, pulse train plus IR, all of those things can be analyzed exactly this way. Okay? We've done some of it. But I just want to point out that we can do the same kinds of things for other fields. Okay? I won't go through that in detail. Yeah, let me just finish by emphasizing this was an exact theory. There's no models, there's no approximations. We aren't using it as a computational tool primarily, but rather as an interpretational tool, a predictive tool. Okay? It's based on simple selection rules, dipole selection, photon number, energy conservation, things like that. Okay? And it can be generalized to other things. Now, I'll also mention maybe not having seen what Tony talked about, but if you take perturbation approximations to this, then I think that overlaps a lot with what Tony was talking about, or will talk about.
My lecture's on the web, you can look at it.
Okay, very good.
You covered this for first and second order cases.
Right, so this is the full sort of exact overarching treatment. if you do the first few terms, say with perturbation theory, that connects nicely with what other folks have talked about. Anyway, I better stop there. Thank you.
Thank you.
A fair number of questions during, I think Brad prodded you to ask questions, but are there more?
I would just make a comment, a clarification. If
Yeah.
you go back to one of the last slides, I think it was under yield.
Oh, okay.
Where you showed the interference between the peaks. There.
Yeah, well, this one's for asymmetry, but
Right.
Okay.
It's asymmetry. So I would just point out that this diagram should also include for the two-photon process, because the tail, the high-energy tail of the two-photon could be above threshold and cause interference.
sure. And so, I mean,
So you
this
don't only start where the central frequency is above threshold.
oh, of course. No, this one could have the tail that extends over there, and that's this guy.
That's right.
Yeah, except in this case, that's actually 0 photon and 1 photon.
Right.
Okay, this
Zero
is-
photon could be absorption and emission.
Exactly.
Not two photon.
And by the way, that maybe is a good point to clarify. When I say 3 photons, that's the net. You could absorb 3, or you could absorb 4 and emit 1, or absorb 5 and emit 2, but that's the net number of photons, okay? And so, yeah, we could actually, from this peak, we could have the tail over here, and that's really what's giving these peaks. So if I were to show the photon peaks, they would lie in these empty areas, okay?
Yeah, go ahead.
Therefore-
and then you ask.
Always there are uncertainty principle between number of photon and phase. If you have information about the number of photon, you lose information about the phase. How is it here? I mean, you know the phase, you know the number of photons. Same.
Oh, but we don't know the number of photons, right?
You say, for example, for this phase, you have 3 photons.
No, I'm saying for a particular phase, I have 0, 1, 2, 3, 4, a whole distribution of photon.
So there are a lot of possibilities.
Absolutely. Yeah, I mean, just like this picture, right? This sketch, I mean, there's several photon peaks contributing.
I mean, first of how you technically solve the Schrodinger equation for an H2 molecule. This sounds a bit complicated. Fundamentally Schrodinger to nuclear ion.
It is, and it's not a short answer, so maybe we can talk later. Yeah. I'll be here till the end of the workshop, so.
School.
School.
So maybe this is a good place to take a 5-minute break, and then we'll come back for the next lecture by Tony, who is not here. Okay, thank you.